analysis of beams by unit load. So as per this method, unit load method, what we are doing, wherever there is a deflection or rotation is required, there apply unit load. So if you require deflection, apply unit load in the direction. If you require rotation, apply unit moment at the direction. Now I will ask you here, the strain energy, from the basics of the strain energy under flexure, the strain energy stored in a body is nothing but integration over m square into dx by 2ei. So this is the 0 to L. Whereas by unit load method, to analyze the beam, analysis means calculation the deflection, delta will be given by 0 to L, capital M, small m into dx by dI. Please note of this. So as per unit load method, the deflection of the beam delta is equal to integration over 0 to L, capital M into small m into dx by ei. Where M, capital M, moment at any section, moment at any section due to external load system. Small m, moment at any section due to applied unit load at required position. So it means that wherever the moment is required, for example, I want a deflection at a point. So wherever the deflection is required, at that point, apply unit load. Apply unit load. E is modulus of elasticity. Of member I of inertia. So here, small m is nothing but wherever the load, wherever the deflection is required, at that point, apply unit load in the same direction. Then you will, if you consider a section, then you will get the moment at any section due to the applied unit load. Due to the applied unit load. Now let us take one problem and we will understand the concept of this. How to solve the deflection at any point by using this unit load method. Now please take one problem. Find the deflection. At the C by using unit load method. by using unit load method. So here the given beam is given, which is having a support A at the one end, and it is having a point load 45 kilonewtons. So AB is the beam with A as hinge support, B as roller support. A point load of 45 kilonewtons is acting 2 meters from left end, 4 meters from right end. So total length of the beam is 6 meters. So this point is C. So find the deflection at C. That means under this point load, they are asking us to calculate the deflection. So here it is typically mentioned it as by using unit load method. It is also another one is there by using real work method or strain energy method also we can solve it. But now we are going to solve using unit load method. In the given data, E is given as 200 into 10 power 6 kilonewton per meter square. I value is given as 14 into 10 power minus 6 meter power 4. EI is constant for the entire member. There is no change in the moment of inertia. EI is constant. So flexural rigidity EI is 200 into 10 power 6 into 14 into 10 power minus 6. So which is 2800 kilonewton square. 2800 kilonewton per meter square. That is the flexural rigidity value. Now in this, the first step, first of all, calculate the reactions. Okay. I'm not writing it as RA by or RAX. Why? Because there is no horizontal load. When there is no horizontal load, here the horizontal reaction is also zero. Is also zero. Now in this, RA plus RB, take sigma Fy equal to 0. That implies RA plus RB equal to 45 newtons. Take sigma M about A is equal to 0 minus RB, taking anti-clockwise as negative minus RB into 6 plus 45 into 2 equal to 0. This will give you the value of RB. Can anyone of you tell me the value of RB here? So RB is 15 kilonewtons and RA is nothing but 45 minus 15, 30 kilonewtons. 30 kilonewtons. So you got the reactions due to the external load system. So the reactions due to external load system. Now prepare a table. The table first one is portion. So why I am doing like this? Just listen here. Here, how many portions are there in the entire given beam? Here there is a change in the loading system. That's why you have to consider it as into two portions. There is a change in the load, so that's why A into C. There is A to C is one portion, C to B is another portion. So AC is one portion, CB is second portion. So, okay, right. You have chosen that there are two parts, AC as well as CB. What is the origin for these portions? Said you are considering the origin. So for AC portion, I will take A as the origin. For BC portion or CB portion, take B as the origin. Come from the support end. So origin is A, origin is B. Okay, right. You have considered the origin as A as B. Let me repeat once again. The given beam is there. In the given beam, we have divided into two portions as there is a change in the loading pattern at C. So that's why AC is one portion, BC is another portion, BC is another portion. Now, what we have to do, origin is to be considered. So from the support end, A is your origin, from the right side, B is the origin. If I say origin, for this AC portion, what are the limits of this? Limits of this one, portion AC, it has a limits of, what are the limits? 0 is, origin is 0, and the end is C, that is a distance of 0 to 2. So 0 to 2 are the limits of the given portion AC. Similarly for BC also, B is the origin, so it is having a limits of 0 to 4. It is having a limits of 0 to 4. Now just listen here. The deflection at any point under the load delta C as per unit load method is 0 to L m into small m into dx by dm. So capital M is moment due to external load system at any section. Small m is moment due to the applied unit load at the point where the deflection is required. So here what you have to do is just take this. This is your beam which is having 6 meters. You want deflection at C, then apply a load unit load at C. So this is 2 meters, this is 4 meters. So we require deflection at under C. So this is 2 meters, this is 4 meters. Can any one of you tell me what is the reaction of this one and this one? Reactions, can we calculate the reactions? RA plus RB sigma Fy equal to 0. RA plus RB equal to 1. So RA plus RB equal to 1. Take moment about A equal to 0 minus RB into 6 plus 1 into 2 equal to 0. RB is 0.33, 0.33 and RA is 1 minus 0.33. RA is 1 minus 0.33. I am not writing any unit for this one. Why? Because this is a unit load. It is 0.67. Now, while writing this, portion AC is written, CB is written portion, origin is considered as A, limits are 0 to 2 for AC portion, then M at any section due to external load system, small m, then EI. Okay. So for this, I want to get what is mx value. So to get mx value, what you have to do is just see this one. Portion AC. So what you consider a section XX at a distance of x from A. Why? Because for portion AC, the origin is A. Hence, you consider a section. This is your RA value. This is your section XX, which is at a distance of x. In between portion AC, just see the diagram. In between portion AC, if you consider a section, here, and it is making a distance of x from A. Now take the left side free body diagram, which is RA. RA value is 30. RA value is 30. So this is 30 kilonewtons. So what is moment at XX? This RA is creating sagging like this. It is trying to create sagging, hence plus 30 into x. You are calculating moment about this point xx. You are not taking moment about a point equal to 0. You are calculating what is the moment at the section. So to get that, mxx is plus 30 into x. 30 is the reaction into distance, which is sagging. So write down the same thing. Mx is plus 30 into x. Plus 30 into x. Now, similar way, for the same portion, you calculate small x value. So this is RA is 0.67. Same section additions of x, but only the change is you are replacing your external load system with your unit load. So which is plus 0.67 x. Just let me explain you once again. So just let me explain you once again. So to get the deflection under the point load 45 kilonewtons, the first step, first calculate the reactions for the external load system. After getting the reactions for the external load system, replace the external load system with unit load and once again calculate the reactions. So after getting the reactions, you have to consider the entire beam into two portions according to the loading pattern. So the entire beam will be divided into as AC and PC. Origin for AC is A, origin for CCB is B, and the limits are AC is having a length of 2 meters, so from 0 to 2 are the limits, and this is BC portion is 4 meters, 0 to 4. Now, capital MX, that is moment due to external load system at any section is plus 30x plus 0.67 into x, that is for M, small m. EI, there is no change in the flexible resistive value. EI is 2800. 2800. Shall I wait for some time or can I continue? If it is completed until this portion, we'll move further.
Yes, sir, completed.
I want the response from everyone in the chat box. Let me wait for a few minutes so that you people, those who have not completed, can complete it. Shiv Prasad, Maruti, are you people able to follow it? Okay, so let us move to the next one. Here, for the CB portion, now once again take the CB portion or portion BC. So take portion CB. Your origin is B, hence consider the free body diagram. Let's right side by considering a section here. Just simply cut a section here, iterations of x from B. Consider a section iterations of x from B and take the right side free body diagram. You can take left side free body diagram also. But here for the easiness, I am taking right side. Now, RB value is 15 kilonewtons due to the external load system. Whereas due to unit load, the value is 0.33 kilonewtons. So now here, capital MXX, that is moment at the section XX due to external load system is, now see this, is it sagging or hogging? This load is from direction. So it is looking like RB into X is sagging positive 15 into X. Whereas due to the unit load system, you have to write down it as M is plus 0.33 X. The load is 0.33, which is making sagging moment as this is 0.33 into X. Now, write these values in the above tabular form. So this is plus 33x, and this value is 2800. A value is constant, hence it is A. Now, total deflection delta at C. Deflection delta C is equal to integration of 0 to L m into small m into dx by L. Now, in this, it is to be divided into two portions, which is 0 to 2. Why? Because just remember here, the integration for the entire system is to be calculated. This, you have two portions. One is A to C, which is 0 to 2 length, and capital M. What is the value of capital M for the AC portion? Plus 30 into X, plus 30 into X, plus 0.67 into X into dx by EI. Integration of 0 to 4. BC portion is 0 to 4 plus 15 into X. That is here. M, capital M into small m. 0.33 into X into dx by EI. Just use your calculator. From this calculator, you can get deflection directly. Apply the integration using your calculator only to simplify it accurately and get the final deflection. All units are in kilonewton and meters. So whatever the distance or deflection you are getting, that is in sorry, in meters. Sorry, that is in meters, and you can convert into in terms of also. Yes, Akshay, you have given an answer as 0.0214. Is it correct for everyone? Please check it. 21.4, is it correct? Or is there any change? You people know how to do the integration. Upon integration, you can use your calculator for this purpose. Otherwise, you have to do it manually. Now, this is very easy step you can do manually. But when there is a lengthy process, then use simply your calculator and get the accurate result. This step 30 into 0.67, that is 20 plus 20 here plus 20 by EI upon integration 0 to 2 x square into dx plus 15 into 0.33, that is 5. 5, 0 to 4, 5 by EI x square into dx. So this is 20 by EI into x square, x cube by 3, the limits are 0 to 2, plus 5 by EI into x cube by 3, 0 to 4. So simplify this, substitute this value 20 by EI into 2 cube, that is 8 by 3, plus 5 by EI into 4 cube, that is 64 by 3. So now upon simplification, what is the value of this? Is it 160 by EI? Is it correct? So delta C is nothing but we already know that is nothing but 160 by 2800. 160 by 2800. So I am getting a value of 0.0571 meters, and the answer is 57.1 Mm, this is the answer. Please check it. Yes, 56.8 mm. Slight changes are there in the values, but however, they are the same. Let's take the next problem and let us try to solve it. Determine the horizontal and vertical component of deflection at A by unit load method. This one is 2 meters. It is having a moment of inertia of I. This is 3 meters and it is having a moment of inertia of 2I. A point load of 7.5 kilonewtons is acting, and here another concentrated load of 15 kilonewtons is acting here. This is the question, and the point A is this one. They are asking us to calculate what is the horizontal deflection as well as what is the vertical deflection at A. So please note on this question. This is regarding the calculation of deflection at any point using unit load method. You can consider this is something like a portal frame, a rigid frame, where AB is the beam, BC is the column. Right. So here what we have to do, there is no required, we need not do any support reaction calculation here, as there is a free end is there. We can start analyzing this one. So just to see, first understand what we have to do here. AB is one portion, BC is another portion. In between B and C, there is no load, hence you can consider BC as a portion. Similar way, A to B, there is no load acting. In between A to B, there is no load acting. At A, the load is acting, at B, the load is acting. So completely AB can be considered as one portion, BC can be considered as another portion. So when you are considering BC as another portion, AB as another portion, here, let us write down. First of all, prepare the tabular form portion. How many portions are there here? We mentioned it as AB is one portion, BC is second one. Now, after portion, what is the origin? Origin for the portion. For AB, what is the origin? I will consider the free end will be the easiest one. So A is the origin for AB portion. Whereas for BC portion, you can't consider C as the origin. Why? Because here the reactions are not calculated. As we have not calculated the reactions, you consider B is the origin. So for BC portion, B is the origin. What are the limits? Next step is limits. So what are the limits you will consider here for AB? Whatever the length is there, 0 to 2. Here this is 0 to 3. Wherever the origin that will be considered as 0 and the remaining portion will be considered, the entire length will be considered. So 0 to 3. Then after MX, please follow this. Now MX is nothing but moment at any section XX in the portion. Now I will just consider this as portion A or AB. So you just consider a section at a distance of x from A. So this is x, this is 15 kilonewtons, this is NDA. Now what's happened to this one? This 15 kilonewton, it is trying to push, inside. So as it is pushing inside, it is creating hogging. See, it is giving a downward deflection like this, which is considered as hogging. So at the portion MXX, that is at the section XX, the moment is here 15 into x will be your moment, minus 15 into x. Minus 15 into x will be considered minus 15 into x. Now, what we have to do, so this at this point, this is minus 15 into x. Why you got minus? The beam, it is being subjected to hogging. Hence, this is considered as minus 15 into x. Now, go for portion BC. Go for portion BC. So to go with portion BC, what will happen? Draw the free body diagram, cut a section, BC portion. Wherever you are writing the momented section, you have to first of all cut the section and represent the distance from the origin. Your origin is B, so X is at a distance of B. Now consider the free body diagram. You can take right side free body diagram, that is top or bottom. Top or bottom, I will take top one, as it is looking like a free end. Here this is 15 kilonewton. This distance is 2 meters. This is 7.5 kilonewton. The distance is x. So this is your cut section. X. Now write down moment at XX. Moment at XX. Just to see this one. Here you are considering your moment. When you consider your moment, this is the point. At this point, the moment is fighting. Here your 15 kilonewton is there. This 15 kilonewton is creating hogging. 15 is creating hogging. Because it is bending like this. It is hogging. Hogging is negative, minus. So we know that the perpendicular distance between these two loads. So 15, this is line of action of the load. This is the point. This distance is 2 meters. Load multiplied with the distance will give you the moment. 15 into 2. So minus 15 into 2. Putting my moment at section XX, which is minus 15 into 2. This 7.5, it is trying to give a moment like this. 7.5, it is trying to move a line like this. So just if the frame is going, this is called as outward and this is called as inward. If the frame is coming towards, that is called as inward. I will tell you once again. So this is considered as hogging only, that is negative only, negative. What is this one? 7.5 into x. This distance is 7.5 into x. Now what is the moment here? Minus 30 minus 7. So when you write moment in a section due to external loads, consider a section at a distance of x from the origin, take the free body diagrams and write the moment at the sections. So for portion AB, what we have done, this is 15 is the load, 15 into x is hogging moment. Whereas for portion BC, from the origin B, why? Because for portion BC, origin is assumed as B. So from B, it is a distance of x. So this is your free body diagram. 15 into 2, 30 kilonewtons is hogging moment. 7.5 into x, which is also hogging. So that's why this is negative. Minus 30 minus 7.5 into x. Now, here the portions due to external, that is, you have written the moment at section XX due to external load system. What they are asking in the question? They are asking horizontal component. First to see the horizontal component. And the next one is vertical component. Horizontal component as well as vertical component. So what we will do is, first of all, horizontal component. Is horizontal deflection. So to get horizontal deflection at A, there is horizontal deflection at A. So what we have to do, remove the external load system and replace, that is entire external load system is removed. Here horizontal deflection, I am just assuming that a unit load of 1 is applied horizontally like this. A unit load is applied like this. So what is the meaning of this one? As per unit load method, wherever the deflection is required, there apply a unit load. So apply unit load at horizontally to get the horizontal deflection. That's it. Simple concept. So to get the horizontal deflection, apply unit load in the direction. So we are assuming that horizontal deflection will happen in this direction. Now, with this, consider a section. So for this is portion AB and this is BC. Now the same section, additions of x is to be considered here. So for portion AB, draw the free body diagram. This is the distance x, this is the section xx. Now this is point A. Here a load unit load 1 is acting. Now what is the moment at xx? See this one. A load is acting. You want to calculate what is the moment at this one. The line of action of the load is passing through the point. Hence, moment is 0. Moment in xx is 0. But here I have to write it as small m. So that is for portion AB, for horizontal deflection, m is 0 here. Get once again. So to get horizontal deflection at A, apply unit load at A in the same direction. So that's why it is applied horizontally in the same direction. And hence, now this point 4 is passing through the point. We require force into distance. Distance is not available. Hence, moment at xx is 0 due to horizontal load. So portion BC. So for portion BC, what you have to do? You need to cut a section here at a distance of x from the origin. B is the origin. Now take the free body diagram. So here this is A, this is B, this is 2 meters, distance of x. So here a unit load is acting horizontally. So what is the moment here? Mxx equal to, this moment is creating hogging. This is hogging, that's why negative minus 1 into x. This is minus 1 into x. So the horizontal one, this is M is 0 for the AB portion, or BC portion, this is minus x. For BC portion, that is now. Is it completed up to this portion? What we have done? We have done for the horizontal portion. So for the horizontal portion, due to the horizontal, there is apply unit load to get horizontal deflection at A. So the formula for horizontal deflection, delta H at A is equal to integration of 0 to L capital M into dx by delta H into A. The delta H at A, that is horizontal deflection at A. So before getting this horizontal deflection, let us go for the vertical deflection also. Vertical deflection at A. So vertical deflection at A. So what happened here? This is your frame, 3 meters length. This is 2 meters. Here apply unit load in the download to get the vertical deflection at A. So this is energy theorem concepts. We have 3 methods. One is strain energy method. Second one is unit load method. Third one is Castigliano's theorem. However, in the unit load method, wherever the deflection is required, the same direction, apply the unit load. To get horizontal deflection, apply horizontal load. To get vertical deflection, apply vertical deflection at A. Now, you have to consider it is as same as the previous one. Consider the section X. I will call it as, so for portion AB, this is your section XX, and this is 1 additions of X A. What is M dash? Why I am not mingling with the M or the same letter? Why? Because this is representation for the vertical deflection. M dash XX equal to, this is creating this vertical load, whatever that is placed, it is creating hogging moment. So that's why this is minus 1 into X, which is minus X. So M dash XX is minus x for portion AB. Write this in the tabular form. Write this in the tabular form. So m dash is minus x, m dash is minus x. Now similarly, portion BC. So once again consider the section here. Additions of x from B. So this is your section XX. Additions of x from B. So the origin is B. So the x additions is to be considered from the origin. So m dash x x. So m dash xx for portion BC. This is regarding the vertical deflection. Now see here, 1 into what is the distance? 2 meters. So here the moment is to be taken at this point. So it is creating hogging only. So 1 into 2, the distance is 2 meters minus 1 into 2. So this is minus 2. So for portion BC, the moment due to unit load, vertical load is minus 2. Write down the same thing. This is your tabular form. Before that, for those who didn't complete, just once again have a look on this vertical deflection at A. Similarly, this is horizontal deflection at A. So to get vertical deflection at A, delta VA, that is vertical deflection at A, is 0 to L, capital M dash into dx by L. So M dash is nothing but moment due to unit load in the section. Capital M is moment due to external load system. So please complete until this procedure. If this is completed, please let me know. We'll move further. For the first time, you people might feel difficulty, but however, all these things will get used. So, Mehraj, are you doing the problem? Just switch on your mic and respond. Om Prakash, are you there? Okay, right, right. Until this portion, if it is clear, we'll move further. So here in the question, vertical deflection at A as well as horizontal deflection at A is asked. First of all, for the given rigid frame, we calculated what are the moments at the section. Yeah, Soumya, you raised your hand. Any doubt, Amma? Right. Okay. I hope you people are attentive to the class. Just don't worry if you don't understand this, you will get used to this. Okay, here. What we have done, just let me explain you once again for the entire problem. It is asked to calculate what is the horizontal and vertical component of deflection at A by unit load method. As this is the free end is available at the A, so take section, that is portion AB separately, portion BC separately. At portion AB, a 15 kN vertical load is acting. It is creating hogging moment, hence it is considered as negative. It is considered as negative as it is creating hogging moment. Whereas this 7.5, it is also creating hogging moment. Towards this side, it might be considered as sagging, but this is considered as hogging. So we got the capital M per portion AB per portion BC. Now to get the horizontal deflection at A, apply unit load at A in the same direction. And the final moment, that is moment due to unit load, is calculated. Similarly, for the vertical load also, we got the values. And here, coming to the table, there is a variation in the flexural rigidity value. So write down the EI value just to see. E value is constant, but I is varying. For AB portion, I value is given as I only. For BC portion, this is 2I. So this is for AB portion, this is EI, whereas this is 2EI. So the moment of inertia is changing 2 times for BC portion compared to AB portion. Horizontal deflection at A, keeps heading horizontal deflection at A, delta A or delta H, horizontal deflection delta H at A is equal to integration over 0 to L, capital M, small m into dx by di. So here there are two portions are there, which is 0 to 2. AB portion, that is m is minus 15 into x into small m is 0 into dx by di, plus what is the next one? Integration of 0 to 3. How you got this? It is depending upon the limits. Depending upon the limits, you will get it. How the limits are obtained? From the origin. What is the distance of the portion? So this is minus 30 minus 7.5 into x, which is capital M value, small m, this is the one small m, minus x dx by BC portion. What is the EA value? 2EI by 2. So from this, if you simplify this one, you will get the horizontal deflection. EA value is not mentioned, so represent the deflection in terms of EI only. So upon simplification, you will get the deflection as 101.25. Please do the simplification and tell me whether this answer is accurate or not. This term has become 0. Don't worry about this term. This has become 0. Only this term is to be calculated, and the answer is this one. So that is right. 101.25 by EI. Students, if you are very familiar with your calculator can do this one. Your calculator can do this one. Simply give integration is available in your calculator. You give it, the entire solution will be given by that. You can directly simply write down it as 101.25 by EI. Now, to get the horizontal vertical deflection, after completing this, go for side heading vertical deflection at A. So vertical deflection at A, that is delta VA, is integration of 0 to L M into, for the representation of vertical deflection, we consider it as M dash. Please wait a second. So here we are calling it as M into M dash. So M dash is nothing but the moment at the section due to unit load applied vertically. Right? So here also you have two portions. 0 to 2 is for portion AC or AB, which is, now go to capital M value. What is capital M here? Just see this one. That's why this table is very, very important. Minus 15 into X, M dash minus X. So minus 15 into X into minus X into dx by EI plus 0 to 4, sorry, 0 to 3. The length is, limits are 0 to 3. M is minus 30 minus 7.5 into X into M dash, small M dash value, minus 2. Minus 2. So this is minus 2 into dx by 2EI. So this will give you upon simplification as 163.75 by EI, which is your vertical deflection at A. Check the answers whether you are able to get the same answers or not. Good. The Sangya has given the answers. Vertical deflection 163. Yes, yes, good. Good, Sai Grams, Manjini. Okay. Now this is the solution how we will do as per unit load method. So how you have done this one? So here you considered portions, and to get the horizontal deflection you applied unit load in the horizontal direction, and to get the vertical deflection you applied unit load in the vertical. So let us once again see the entire problem. Yes.
Sir, horizontal ఒకసారి calculation the integration నాకు రావట్లేదు.
Okay. So see, for the horizontal deflection, what we have taken 0 to L, capital M into small m into dx by EI. That means you want,
sir, అంటే calculation చేయరావట్లేదు అది.
okay,
Values okay, sir.
Okay. You want to do manually, right?
Yes, sir.
So here somebody is asking to do it manually. This portion, just take this one. I will take it outside. Just I am writing here 0 to 3 minus 30 minus 7.5 into x into minus x into dx by 2e. This is minus 30 into minus x, 30x, plus 7.5 into x squared by 2EI, integration over 0 to 3. So 30 into x, integration of x is nothing but x squared by 2. 1 by 2EI is constant, I will keep it like that. 30 into x squared by 2 plus 7.5 into x squared, x cubed by 3. The limits are 0 to 3. So substitute the limits here. 1 by 2 EI into 30 into 3 square by 2 plus 7.5 into 3 cubed by 3. So this is 15 into 9, 135 plus 9 into 7.5. Am I audible?
Yes, sir.
Yes.
Okay, sir. వచ్చింది sir.
All of you, are you able to complete this or not? Just don't get confused. See once again, look after the entire problem. I think wherever you require, you can zoom it. Please once again see the entire portion, entire problem for 2 minutes. I'm just giving a break. If I give a break, you people are leaving. That's up to you. I'm giving a break up to how much time you require. I have to continue the next class also. Rahul,
Sir,
how much time you require the break? Shall I give the break or shall I continue?
కంటిన్యూ చేసి 1:30 1 వరకు ఆపేయండి సార్. బ్రేక్ ఇప్పుడు ఆల్రెడీ అయిపోయింది కదా సార్.
ఓకే రాహుల్ చెప్పాడు కాబట్టి మన రాహుల్ మాట అయినా ఇప్పుడు. Okay, let us take the next problem. Determine, let us move to the next problem. Determine the vertical deflection at midspan. EI is given as 3 into 10 power 4 kilonewton meters. A, B, C. It is loaded with AUDL, which is 15 kilonewton per meter. This is EI. This is 2EI. Distance is 2 meters here. This is 2 meters. Okay, for this, what they are asking to get the vertical deflection at midspan, that is at B, they are asking us to calculate. As it is a simple supported beam, first of all, calculate the reactions. Calculate the reactions. So total length of the beam is 4 meters. The load acting is 15 kilonewton per meter. So now see this one. It is a symmetrical one. Hence, the total load is 15 into 4, 60. 60 is equally to be distributed. 30 kilonewton. This is 30 kilonewton. Here at the hinged support, there is no horizontal reaction as there is no horizontal load. As there is no horizontal load, there is no horizontal reaction. Okay. So in this, what we have done, the first one is 15 kilonewton per meter is the load acting. So that load, it is a symmetrical beam, something like this. You can understand it typically. A UDL is acting here, 15 kilonewton per meter. This is B point. This is support C, RC. RA is 30 kilonewtons. RC is 30 kilonewtons. This is 2I. This is I. I moment of inertia for AB portion is I. Moment of inertia for BC portion is 2I. Now in this, as there is a change in the moment of inertia, you have to consider two portions separately. The loading is uniform, but there is a change in the moment of inertia. Hence, you consider this into two portions. AB is one portion, BC is another portion. So separate them into two portions. So now, what you have to write down? Portion is AB is one thing, BC is the next one. So after this, after portion, write down what is the origin. Generally, for AB portion, A is the origin. For BC portion, C is the origin. From the support end, you can consider the origin. Now, limits. What are the limits? For length is AB length is 0 to 2, BC 0 to 2. Limits 0 to 2, 0 to 2. Now, what we have to write down? M, Mx is moment due to external load system at any section. Then small m due to the applied unit load after removing the entire loading system. Then the last one is EI, flexural rigidity. For AB portion, EI is EI only. For BC portion, this is 2EI. For BC portion, this is 2EI. Now, what you have to do to get MX? Consider portion. This is your UDL. 30 kilonewtons is there here. This is your X. This is your section X. This is 15 kilonewton per meter. Now, can any one of you tell me what is MX value? Moment at X. I'm just waiting for an answer. What is the moment at section X?
So 30x minus 15x square by 2.
30.
30x minus 15x square by 2.
30x minus 15x square by 2. Good. So here you are considering a section. 30 into x is giving sagging moment, hence it is positive. Plus 30 into x minus 15 into x square by 2. So that is the answer. Write on the same thing. 30x minus 15 by 2 is nothing but 7.5. 30x minus 7.5 x square. Okay, now portion AB is completed. MX is got obtained. Now go to BC portion. Portion BC. Here also origin is C. Hence cut a section here at distance of x from C. So write down the free body diagram towards right side. This is our RC 30 kilonewtons. UDL is acting. Is 15 kilonewton per meter. The distance is x. Here this is the moment is nothing but 30 into x, which is sagging, minus 15x squared. So 30x minus 7.5x squared. That are given moments in external load system. Now, to get this small m, replace the entire external load system. This is your beam A, C. Replace your entire system with a unit load, and the unit load is required at B. So apply unit load at B where the deflection is required. Now, in this one, as this is 2 meters, you can simply understand this one, this is 0.5. Now consider the section, relations of x. Once again, go to the portion AB. This is 0.5. This distance is, so small m is 0.5 into x. See, there should be a difference between capital M in your writing also. Don't write this as like this. It is to be written as small m, which is 0.5 into x for AB portion. Similarly, consider a section at a distance of x from C. So coming to the portion CB also, the free body diagram, this is 0.5. The distance is x, and small m is nothing but sagging only. Why? Because they are trying to go sagging, which is 0.5. Is 0.5 into x. The series we got the moments. Now deflection delta p is equal. This is vertical deflection only. That's why I'm not then specifically mentioning it as delta v. Is vertical deflection delta b is integration of 0 to L m small m into dx by dy. If there are horizontal and vertical deflections, then we are representing them as m dash for the other one. One is m, another one is m dash. Now, this is 0 to portion for 0 to 2, 30 into x minus 7.5 x squared. Yeah, just due to the place, I will write down here. 30 into x minus 7.5 into x square into 0.5 into x into dx by ei. This is ei plus 0 to L. We are writing for PC portion. 30 into x minus 7.5 into x square into 0.5 into x into x by. So here this is to be substituted. Okay, you will get delta V value. Just check it and tell me that. Okay, got it right? 37.5 by EI. So the final deflection is 37.5 by I. It is given EI value is 3 into 10 power 4 kilonewton meter square in the question. You can substitute that one, that is 37.5 by 3 into 10 power 4. So you will get the answer in terms of meter. Please be consistent with your units. You get it as the final answer. So you will get the deflection as 0.00125 meters or 1.25 mm. Multiply with 1000 to get in mm. 1.25 mm. So due to the application of the load, unit load, that is UDL 15 kilometer per meters, the deflection is 1.25 mm. This is how we will solve as per unit load method. As per unit load method. If anyone is having any difficulty, you can take now the screenshot of this one. Entire problem is visible to you. Yeah, Mavia, are you able to understand it? So this is how we will solve as per unit load method. Let me give you some problems for your exercise. Note of the problems. You can solve it and try whether you are able to get the answers or not. Find the central deflection of the beam shown in figure. E is equal to 2 into 10 power 5 Newton per mm square. I is equal to 80 into 10 power 6 mm power 4. So this is the problem. Here there is a change in the moment of inertia, hence why that is given like this. Here the supports are like this. So central reflection means at E, the reflection is to be calculated. At E, there is a concentrated load which is 100 kilonewtons. Here this moment of inertia is 2I, this is I, this is I, and each portion is having a distance of 2 meters. Here understand, to solve this problem here, first thing is there is a change in the loading pattern from AE to DEB. From here to here, there is a late load change in the loading pattern. Load is acting. Hence, you need to consider AE as one portion, EB as another portion. In between AE, here there is a change in the moment of inertia. So the portions will be now 4: AC, CE, ED, and DB. 4 portions you will get. This is one problem. Please do practice of this part. Find the vertical and horizontal deflection at point C of the frame